Morning. Okay, so your exam will be next Tuesday. It will be during class time, so your exam will be on Blackboard at 9:15. So make sure you join the Zoom meeting beforehand, and once you turn on the camera by 9:15, you can start the exam on Blackboard. So the mock exam the exam will be similar length as the mock exam. You do need to have your camera on. So once you turn on the camera, you may start the exam. As people asking, if it happened that your computer disconnect, try to connect back as soon as possible, and you can log back into your Blackboard. And the Blackboard should automatically save your answer, so you can continue from there. Any other question related to the exam? Okay, if not, I will just go over the question on the mock exam first. I hope everyone did it already. Can everyone see the question? Okay. So here's like a true false question. So it's asking is the propositional so here you have a propositional function and you want to check for there exists x and where the domain is consists of all the integer. And you want to check, does there exist an integer x so that your propositional function is true. Okay, so you have x is less than 6. You have conjunction 3, x is greater than 21. Now conjunction here means and. That means you want to have your x satisfy both conditions. Now if you look at this inequality here, 3x greater than 21, that means you can simplify, divide 3 on both sides, so you can have x is greater than 7. So you have x is less than 6 and x is greater than 7. Can you find any integer x where x is less than 6 and greater than 7? No, so the answer is false. Okay, I see people asking, can you go back to the previous question? Yes, if you look at the arrow here, right, this single arrow allows you to go between the question, and then the double arrow will take you to the first question, then last question. So be aware you where you clicked it, and after the last question, you will be able to save and submit the exam. So before you finish the exam, don't accidentally submit it, because once you submit the exam, I can't change anything. Okay. Now, this question asks you to state the negation of the proposition. The integer x, the integer n is odd, and n is at least 7. Right, so you want to negate the statement. So if you look at this statement have 2 parts, right? You have an integer x, you have integer n that's odd, and you have n. So you have n is odd, and you have n, it's at least, means it's greater or equal to 7. So you have an and relation here. Now to negate it, you need to apply the De Morgan's law. So negate each part. And then you also need to negate the conjunction. And all your answer will be inside the text box. Right, so to negate the integer is odd, then you will have the integer n is not odd, means it's even. Now you have this n here, right? To negate n, you will have or. And you have or, and it's not at least 7. Not at least 7 means your n will be, so negation of at least 7, you will get your n it's less than 7. Now I see people saying, what if you say not odd? You could say not odd, but normally for not odd, we will say it even. Okay, so this question, like we did the STEM question in class. So this question asks you just to state the inductive hypothesis and to state the statement you're trying to prove after that. So it asks you to state the statement that you need to prove to complete the induction, but you don't need to prove anything. You just need to state the statement. So part A asks you to state the inductive hypothesis, which we will assume So the statement is every amount of postage of 12 cents or more, this is a or, there's a typo there, can be forwarded using 3 cents and 5 cent stamp. So to have the inductive hypothesis, you will assume the K cents postage. So assume K cents postage can be formed using 3 cents and 5 cent stamp. Now you need to be aware, you need to give a parameter for K, because what's the parameter for K, right? So K will be the same parameter as the question, right? So your N. Now here we have for every amount of postage of 12 cents or more. So we know K will be at least 12. So don't forget your condition on the variable, right? So that's part A. Now part B, it will ask you to state the statement that you need to prove to complete the induction. So after the your assumption, right? So normally we assume K, and you want to prove Pk plus 1. So you want to show K plus 1 cents postage can be formed using 3 cents and 5 cents stamp. So that will be the whole question. Any questions here? Okay, now here it asks you to prove or disprove via counterexample that the product of any 3 consecutive integers is divisible by 4. So is this statement true? Okay, I see people say no. If no, can you give a counterexample? Okay, I see people say 1, 2, 3. So you can say this statement is false. Now you need to explain it. So you can say 1, 2, 3 are 3 consecutive integer. 1 times 2 times 3 equals to 6. But 6 is not divisible by 4. We found a counter example which disproved the statement. Right, so here's your explanation. Next. Okay, it's asking which of the following logical propositions are not equivalent to P implies Q. Well, if you look at it, P imply P if and only if Q, that means P implies Q, and also Q implies P, right? That's what double implication means, or biconditional statement. And we also know if P is true, Q must be true, which means if P is false, Q must be false. So that means you will have either P and Q, or not P and not Q. So this means they are either both true or both false. Okay, so we know that the okay, I see people say the second one. What about the second one? Now also, if you try to write the implication here as the so if you rewrite it, so you don't see the implication. So P implies Q means you will either have not P or Q. Wait, not P and Q. Or you will let's see. So you have not P or Q. That's what, so P implies Q. It means you will either have not P or Q, right? Since if P is true, then you know Q is true. Otherwise, you have P is not true. So you will either have not P or Q. And Q implies P, that will give you Q implies P, that will give you not Q or P. So you have not Q or P. So you know this statement is when the statement is true, but the question asking you which of the logical propositions are not equivalent to P implies Q. So if you look at it, we have P implies Q or P Q implies P, and we know this is false since it needs to be conjunction. Both need to be true, right? P implies Q and Q implies P. Now, if you look at the second one, you have P or Q and not P or not Q, and we know this is false. Okay, and then and the next one you have not P and Q or P and not Q. Or if you look at that, you probably you might not know is this one true. So let's leave it there for now. And then you have P and Q or not P and not Q, and we know that's a true statement. We'll have P and Q or not P and not Q. So we have this one, so we know this one is true. And then we have P implies Q and Q implies P, and we know that's a true statement, so that's the first one. And then we have the last one, you have not P or Q and P or not Q. Right, so that's the last statement here. So we know this is also true. Okay, I see people asking, how do we get P and Q or not P and not Q? Okay, so this is saying, okay, so we know P if and only if Q is true if they are both true or both false. So P and Q you can think of when they are both true or they are both false. So you either have P and Q or you have not P and not Q. Okay, so the question here again, it asks us to select the one that's not equivalent to P if and only if Q. Okay, now if you look at the second one, okay, so here's a, let's see. I might make a typo here, right? On one of this supposed to be false, but in here, these two statements are the same, right? So we just show that. Let's see. So we just show that not P or Q and not Q or P is true. Right, so that's from P implies Q and Q implies P. Now, if we negate it, you will get negation of not P or Q or negation of not Q or P. And then you will apply the De Morgan's law again. Then you have P or not P and not Q or Q and not P. And that will be the second statement. So there's only two statements that's false. So it's it might not be easy to see the third one is also true. Okay. The next one, you have the propositional function x cubed is less than y squared, and then all the variable here consist of the integer. So we want to check the choose value for there exists an integer x for all y, x cubed is less than y squared. So can you find an integer for x? So when you cube the number, that's always less than y squared for any integer y. Anyone? Okay, so I see people say when x is 0. Well, if x is 0, is 0 less than y squared for all integer y? Can y also be 0? Zero is an integer, right? So what if y equal to 0? Then this is not true. Is there any other value work for x? Anyone? Okay, if you let x to be 1, then you have 1 cube. You have 1 less than 1 squared. Again, if you let y equals to 0, it's false. Okay, I see people say -1. If you have -1 cube, you will get -1. And -1 will always less than y squared, since y squared can never be negative, right? Y squared will always be greater or equal to 0. So if you let x to be any negative number, it will be true for all integer y. So this is a true statement. Okay, next, again asked to determine the truth value for the statement. If 120 is prime, then 2021 is even. Is the statement true or false? Okay, it's true. Why? If you check, is 120 a prime? No, right? So since if it does not pass the hypothesis, like the if statement, then you don't even need to check the rest of the statement, right? Because when you have an implication statement, you need to check the conclusion if it satisfies the hypothesis. Right, and I see people put it in the chat, right? If you have a false statement, imply a false statement is true, according to the truth table for conditional statement. Okay. Now, if you look at this statement, so this is the one we prove in class. At least 4 of any 22 days must fall in the same day of the week. So is this true or false? So we know this is true, right? Because in class we proved it. But how do we prove it? Which proof method we did to show this is true? It's an induction. Did we do an induction on this statement? Did everyone agree with that? We use induction to prove it. Okay, so for people who say we use induction to prove it, what's the base case here? Anyone? Okay, so I see people say it's a contradiction, right? It's not induction. Right, so if you look at it, it's saying that at least 4 of any 22 days. And we do induction question normally when you're trying to prove a propositional function where the variable is in the some integer ranged, right? Maybe positive integer, non-negative integer, integer greater or equals to something. So for this statement, we will first assume the negation of the statement. Right? We will assume at most 3 days are on the same of the on the same of the week for the 22 days. And then we show that it cannot be done because if you put down at most 3 days, then you can at most select 21 days, but you have 22 days. So we prove it by contradiction. Okay, so this is a long answer question. It asks you to prove the statement. Okay, so you want to prove that if x squared plus 4x minus 6 is even, then x is even. Right, so this is what we're trying to prove. But if you look at that, we want to start on the right-hand side. So we will prove by contrapositive. Right, so you need to stay wherever the proof method you are using. Then the equivalence statement will be you want to prove x is not even. That means x is odd. So you want to show if x is odd, then x squared plus 4x plus minus 6 is not even, which means also odd. Now, since x is odd, we can write x as 2k plus 1 for integer k, right? You need to define your variable. So you can just say k, otherwise k can be 0.5, right, a fraction. Then x squared plus 4x minus 6 will equal to 2k plus 1 squared plus 4 times 2k plus 1 minus 6. Which you can get 4k squared plus 4k plus 1 plus, now you distribute the 4, you will get 8k plus 4 minus 6. Now if you combine the like term or simplify the equation, you will get 4k squared plus, you have 4k plus 8k, so you get 12k. And you have 1 plus 4 minus 6, you get minus 1. Now, if you want to put it into the odd number form, then you can factor out 2 times 2k squared plus 6k minus 1. So you can either put it as 2k minus 1 is fine. That will 2k plus 1, 2k minus 1, they both represent odd. So you can either do that, or you can do 2 times 2k squared plus 6k minus 1 plus 1. They are the same. So either way, you show that it's odd. And this is how you finished the proof. Any questions here? For this question, I would say the easiest one is to use contrapositive. Or you will do it by cases. You will do when x is even, when x is odd, and you will say this scenario will only happen when x is even. Only when x is even, this is even. Otherwise, if x is odd, you won't get this to be even. It's kind of redundant to show it the other way, because the other way you need to do everything here as well. You need to show when x is even, and you also need to check. So pretty much you check when x is even is true, right? So you kind of just do it when x is even, this is also even. But if you just do that, it's not enough to show the statement. So for the control part, you kind of just need to show one case. Okay. So this is the way we will prove it. So whenever you see like an if then statement, like implication statement, normally you will decide between the direct proof or contrapositive. Now, unless your both statement is equally hard and you can start anywhere, then if the question is about the parity, about even odd, then you can do a cases. You can do when x is even, and then to show this is even, when x is odd, this is odd, and then show that the only scenario that for this statement to be even is x is even. Otherwise, you will get odd result. Then you will do this proof all over again for even. Good. Okay, so here is the induction question. So for induction question, right, you always start with the basic step, right? And then I upload the induction notes on Blackboard, so you should know how to type your solution. All right, so for basic step, your n will start at 1 in this case, since your n is a positive integer. Now, when n equals to 1, your left-hand side, when you plug 1 into 4 times 1 minus 2, you will get 2, and 2 is your first term. So you only have one term. If 2 is not your first term, then you need to start at your first term and then end there at your last term. Now, it just happened that your last term here is also your first term, so you stop there. Now, the right-hand side, you have 2 times 1 squared. And that will give you 2 equals to 2. And notice that if you want to do indentation, or if you want to have space, you can only type space. You cannot use tab. Tab key does not work in the text box. Okay, so this is your base case. You show that they equal to each other. Then you have your inductive step. Which you need to make the inductive hypothesis first. You will assume two plus 4 plus 10 plus 14 up to 4k minus 2. This will equal to 2k squared for integer k, or you can say for k greater or equal to 1. And then you want to show 2 plus 6 plus 10 plus 14 up to 4 times k plus 1 minus 2. Plus equals to 2 k plus 1 squared. Right, so this is what you're trying to prove. Now, if you look at the last term here, you have 4k plus 4 minus 2, which means you have 4k plus 2. And you want to show this is equal to 2 times k plus 1 squared. Then that means you have 2 times k plus 1 squared, you will get k squared plus 2k plus 1. Now the term before the previous term, right? Normally we know to do the proof by induction, somehow you need to apply the hypothesis, which you know was the sum of first k term. So you know what's the answer from 2 up to 2k minus 2, but you don't have 2k minus 2 here. Now, if you look at the pattern here, you see we are incremented by 4 each time, right? From 2 to 6, you add it by 2. From 6 to 10, you add 2. And then from 10 to 14, you add another 2, and so on. So if you get the term before 4k plus 2, that means you need to decrease by 2, since you increment it by 2 to get the last term. So the term before that, it will be 4k plus 2 minus 4, then you will get 4k minus 2, and that's your previous term here. Now you see so here is your sum of first k term. And then you add in the last term equals to 2. Now you can distribute the 2, so you have 2k squared plus 4k plus 2. Now if you look at it, by inductive hypothesis, you know the sum of first k term here. I put it in box here. That will equal to 2k squared. So you will have 2k squared plus the last term, 4k plus 2. And you want to show that's equal to 4k squared plus 4k plus 2. And we show that the left-hand side, you get 2k squared plus 4k plus 2. That will equal to 2k squared plus 4k plus 2. So we show that left-hand side equals to the right-hand side. Any questions here? Okay, next it asks, which of the following statement are a proposition? Well, if you look at it, good luck is not a proposition. God bless you is not a proposition. X plus Y, you have a variable, is not a proposition. What time is it now is a question, is not a yes, no, or true, false statement. And again, integer n is greater than 120. You have a variable, so it's a propositional function, not a proposition. 120 is odd, is a proposition, but we know it's false. So as long as you know it's false, you know it's a proposition. Questions here? Okay. Now here we want to show integer are not closed under division, right? In other words, we want to show that if you take an integer divided by an integer, it's not always an integer. So to prove it, right, so this will be proved by contradiction again. But we did a similar proof in class where we showed that exponential integer are not closed under, no, we checked that irrational are not closed under exponential. Right, so we want to assume integer is closed under division. This means which we have we want to show integer divided by, which will assume integer divided by integer is always an integer. Then what? How do we contradict our assumption? How do we show that integer divided by an integer is not an integer? So our goal is trying to disprove or contradict the assumption. So how do we do that? Anyone? Okay, so I see people have counterexample 1/0 is not an integer, right? Or you can say 1/2 is a fraction, not an integer, right? So we can say 1 and 0 are both integer. 1/0 is not an integer. There's contradict with the assumption. So since it contradicts with the assumption, therefore, the original statement is true. Right, so you can give other counterexample. So just found a counterexample where when you divide it, it's not an integer, and you explained it. Okay. But you need to write out the whole statement. You can't just pull out a counterexample. Right, because if you just give 2/5 is true, then you are only showing one example. It's not enough. Okay, so here you're asking on which of the following propositional logic are equivalent to P implies Q. Well, we know not Q implies not P is true, right? That's the contrapositive. And then we can also have, we can either, if P is true, then Q is true, or we can have not P, right? So we know we can have not P or Q. So the last two is true. Okay, so here are three propositions. So one is we should be honest, Q is we should be dedicated, and R is we should be overconfident. Now, here is, so you want to find the notation for we should be honest or dedicated, but not overconfident. So here we have like a disjunction, we have all relation. So we have P or Q, but not overconfident. So but here it actually means and, right? So you should be honest or dedicated, but not, which means and not overconfident. So you are negating the R. So you should have P or Q and not R. So you have P or Q and not R. So that will be the choice. Okay, so this is similar to the first example we did. So we have x is less than 6 or (3x) is greater than 21. Now saying that we want to check is it true for all value x? This is true. So is it true that for all integer it's less than 6 or 3x greater than 21? We can write that as x greater than 7. So is it true that your number will be less than 6, like for all the integer will be less than 6 or greater than 7? Okay, I see people say no. If not, can you give a counterexample? Okay, it cannot be 6 and 7, right? 6 is not less than 6 and it's not greater than 7. Same thing at 7, right? So 6 and 7 is a counterexample, right? Since we say for all integer x, we want it to be true. So this is false. Okay, so you have another induction question. Again, you have basic step. Now here we have n is greater than 6. So that means your n need to start with 7. Now you need to compute 3 to the 7 at less than 7 factorial. Now you can calculate it to show this is true. Right, so what's 3 to the 7? Well, 3 to the 7, not 3 times 7. This may have 3 times 3 times 3 times 3 times 3 times 3. I think I have 7 3 here. You want to show this? It's less than. You can use a calculator on the exam as long as you show all your work. Okay, so I see people say 2187. Now what about 7 factorial? Okay, so you have 50, 40. So you know this is true. And then you will have your inductor step. Again, you will make inductor hypothesis, which you will assume 3 to the k is less than k factorial for k to be greater than 7. So that means your k need to be greater or equals to 7. And then you want to show that 3 to the k plus 1 it's less than 7 factorial. It's less than k plus 1 factorial. Right, so this is what we want to show. Now, if you start with 3 to the k plus 1, well, we know 3 to the k plus 1 can be written as 3 to the k times 3. And we know that by inductor hypothesis, we know this is less than k factorial times 3. And you want to compare with k plus 1 factorial. And we know this is less than k plus 1 times k factorial times k plus 1. Since we know k is greater or equals to 7, then k plus 1 is definitely greater than 3. And we have this k factorial times k plus 1, that's equals to k plus 1 factorial. So we show that this is true. Right, so we show that 3 to the k plus 1 is less than k plus 1 factorial. Right, so this is similar to the example we did in class. Next is saying that for all integer value x, x squared plus x is even. Right, so this will be, so you want to show for all value x, x squared plus x is even, right? So it's about even odd quotient. So this will be approved by case, right? So it will be proved by cases. All right, so we want to check, we want to show x squared plus x is even for all integer x. So prove by case, well, case one will be x is even. Now if x is even, you can write x as 2k. Again, k is integer. Then k squared plus, x squared plus x will equal to 2k squared plus 2k. Then you will get 4k squared plus 2k, which you can write as 2 times 2k squared plus k, which this is even. Now case 2, you can have x is odd. Now if x is odd, your x squared plus x will equal to 2k. Your x can be written as 2k plus 1. Again, k is integer. Now you can write x squared as 2k plus 1 squared plus 2k plus 1. Now you will get 4k squared plus 4k plus 1 plus 2k plus 1. And then you will get that simplifies to 4k squared plus 6k plus 2. And you can write that as 2 times 2k squared plus 3k plus 1. Again, so you'll write as 2 times the integer. This is even. So you know, no matter what your x value, x squared plus x is always even. So we know that for all integer x, x squared plus x is even. And we will finish the proof here. Any questions here? Okay, the last one, you want to state the negation of the proposition. There exists an integer x such that x less than y for all positive integer y. So you have there exists. So to negate there exists, you will have for all integer x, and then you have such that x less than y. So if you look at the original statement, you have there exists x, and then for all y. right? For all y, and then you have x less than y. Now to negate it, so this is original statement. So to negate it, you will have for all integer x, and then for all y, when you negate it, you will have there exists. So when you negate it, you will have for all integer x, there exists an integer y such that, and then you will need to negate x less than y. So to negate x less than y, then you have x is greater or equals to y. So this will be the negation of the original statement. Any questions here? I see people asking, can you put for some positive integer y at the end instead? So you are saying for all integer x such that x greater than equals to y for some integer y. Well, you could do that, but when you read it, it will sound awkward. For integer x such that x greater than y for. Yeah, when you do that, it will sound weird. Like you will not know which one comes first. For integer x such that. Like if you say that, if you have that statement, this statement will be very confusing. So normally we don't put like for some integer x at the end. We will say like there exists, and then we will put that in at the beginning. Right? Because if I ask you to prove a statement like that, and then if I write the statement like for all integer x such that x greater than y for some positive integer y, it will confuse a lot of people. So instead of just negate it, you also need to make it sounds right. Okay. I see people asking why is the negation greater or equals to not greater? Well, what's the negation of less than? Right? If you do greater than, you are missing a value. Where is y? Right. So when you're negating x is less than y, that means you want to take the value that's when the statement is false. So when x equals to y, then your x is not less than y, then it should be include, right? Your y is not less than y, so it needs to be included in the negation. So the negation of greater than it's less than or equals to, and the negation of less than will be greater or equals to. You need to include all integer. Okay, so this is your whole mock exam, right? So this will give you an idea of how the actual exam gonna be. Right, in fact, this is previous semester's exam 1. Is there any other question? Okay, if not, we will end it here and I will see everyone next Tuesday. Okay, so make sure you join the Zoom meeting before class start, like before your exam start, so you can turn on the camera and then start the exam. Okay, everyone have a nice day.